Hello, everyone. This is Shashank Modi from the Center for Automotive Research. Welcome to the first battery enclosure design webinar. We have a lot of people joining in right now, so we're going to wait for 2 minutes and then start this webinar. Thank you. Let's just give one more minute. We have still a few people joining in. All right. Sarah, do I have permission to present?
Yes, you can go ahead and share your screen.
Okay, thank you. Let me try that. So welcome everybody. This is Shashank Modi from the Center for Automotive Research. We are here for the Battery Enclosure Design webinar series. This is the first webinar in the series, and we have a great speaker today, Dr. Andreas Afseth, with us, who I'm going to introduce in just a minute. But this is a three-part webinar series, and experts will present on three different materials, that is aluminum, steel, and polymer composites designs for battery enclosures. And today we will have a presentation from Dr. Andreas Afseth. He is the technical director at Constellium, North America. Dr. Afseth is a technical director for automotive body sheet of Constellium North America operations. He's based in Plymouth, Michigan, where he leads the engineering and technical service teams responsible for product development, product launches, and field support. He has 25 years experience in aluminum and automotive industries, and he began his career at Constellium, where when Constellium was not named Constellium, it was Alcan. So he has been with the company for a long time. He holds a PhD in material science as well as the Master of Science in Chemistry from the University of Trondheim, Norway. I hope I said that right, Andreas. So welcome, Andreas, and thank you for your time today. And with that, I'm going to hand you over the presentation. But before that, I just want to remind everybody that we want to keep this webinar as interactive as possible. There is a Q&A box in the webinar that you can type your questions in. And please keep your questions coming because we don't plan to do a a presentation and then a Q&A session. We plan to have discussion as we go along and for the entire 1 hour that we are here. Okay, so Andreas, you can go ahead.
Great, thank you very much. And your pronunciation of Trondheim was pretty close to correct.
Oh, thank you.
Yeah, so thank you very much for the kind introduction. I'll see if I can share my screen. There we go.
Yeah, that's perfect.
Yeah, so over the next hour, I'll try to walk through these points. So I'll first do a short introduction of Constellium, so you understand who we are and what we do. And then I will talk about how aluminum is used today in battery electric vehicles, and specifically in the battery enclosures, and also a bit about how we see this evolving in the next few years. Then in terms of explaining why aluminum is used the way it is today, I will talk through the different drivers for material choice and lightweighting in battery electric vehicles. And then I will go into some more technical detail on the battery enclosure, showing some of the designs, some of the design criteria, and explain a bit of which aluminum alloys and products are currently in use, and also show a couple of developments that are in progress that will be coming to the market in the next few years. So Constellium, while the name is relatively new, parts of the company date all the way back to the inception of the aluminum industry more than 100 years ago. So we have long experience. Today, we're about 13,000 employees worldwide, spread over 28 production facilities. We also have 3 R&D centers, and the annual revenue was just under 6 billion euros in 2019. So in dollars, it's a little bit more than 6 billion. Then in terms of the product forms and the solutions that we offer, we make rolled plate and sheet. We also make extruded profiles. And we also design, engineer, and manufacture structural components as a tier 1 supplier to the OEMs. Finally, we are one of the biggest recycler of aluminum scrap, where we buy scrap back from the market, remelt it, and turn it back into full value-add aluminum products. This roadmap, sorry, struggling a bit with that, shows the locations we have. And as you see, we are relatively heavy focused on Europe and North America, but we also have 2 automotive structure manufacturing plants in China, serving our customers there. In North America, we have 2 large rolling mills, one in Alabama, one in West Virginia. We have an automotive heat and surface treatment line in Bowling Green, Kentucky. We have an extrusion plant in Ontario, Canada. And we have 3 automotive structure manufacturing plants in Michigan, Georgia, and Mexico. And then we have 1 R&D center right here in Plymouth, Michigan, where I'm sitting at the moment, which is dedicated to supporting automotive customers in North America. We also have 2 large research centers in Europe. Outside Grenoble in France, we have Europe's largest industrial aluminum research center with full-scale prototyping capabilities for all aluminum product forms. We also have Constellium University Center, which is a lab situated on the campus of Brunel University, right next to Heathrow Airport in London, UK. And this is dedicated to extrusion technology and prototyping of automotive structures. So in terms of the products we sell into automotive industry, we make auto body sheet for use in the body in white or in the closures. We also sell decorative sheet used in automotive trim and bracing sheet used in heat exchangers. On the extruded product side, we do sell extruded semi-products for OEMs to use in the body in white, and we also make engineered structures for use in the body in white, crash management systems, and as we're talking about today, a growing market in the battery enclosures for battery electric cars. So that explains Constellium and what we do. And I will now talk about how aluminum is used in battery electric vehicles today, with focus on battery enclosures. Most of the data I show here comes from a recent study done by Ducker Frontier. It was commissioned by the American Aluminum Association and published in August of last year. So the main findings of the Ducker study is that aluminum continues to be the fastest growing material in automotive application, and that the growth that we see from 2020 over the next decade is driven mainly by two separate things. The first is the continued substitution of steel in the body in white and body panels of conventional powertrain vehicles. And the second is the increasing market share of battery electric vehicles, which already utilize a lot more aluminum than the conventional powertrain ones. So when we analyze the aluminum content in vehicles, we separate between what we call platform parts and component parts. The platform parts are those that form the vehicle structure, so the chassis, the body in white, the body closures. And for battery electric vehicles, the battery enclosure is part of this because it forms an integral part of the vehicle structure. The component parts are all the add-on parts to the vehicle structure. So powertrain, driveline, brakes, wheels, and the like. A lot of the aluminum that's used in conventional powertrain cars are castings in the powertrain. So the engine block, the cylinder heads, the transmission case, these are all heavily aluminum. And this, of course, will disappear when we move to battery electric vehicles. They are replaced by some component parts like the housings for the electric motors or the inverters, but these are much smaller and make a smaller contribution. So when we compare how much aluminum is used in the average battery electric vehicle produced in North America in 2020 to that of the ICE or hybrid vehicle, you see there's a huge increase with more than 640 pounds of aluminum per vehicle in the battery electric vehicle and only 450 pounds in the conventional powertrain ones. We also see there's a huge difference in where in the vehicle the aluminum is used. So for the ICE vehicle, the bulk of the aluminum is in the large castings for the powertrain, and only about 136 pounds of aluminum is used in the body in white and the body closures. And comparing this to the battery electric vehicle, this ratio is completely inverted. There's much less aluminum in the component parts, only 200 pounds, but there's more than 3 times as much aluminum used in the platform parts, which means the battery enclosure, the body in white, and the body closure panels. And then in terms of how we see this evolving in the future, the study shows that in fact, in terms of purely in terms of pounds per vehicle, aluminum has already peaked. And what we will see over the next years is that we'll see slightly less and less aluminum in the average vehicle. This is linked to launch of new models and also smaller cars with moderate range, targeting the lower price ranges. We see them going more towards a multi-material design rather than being aluminum intensive. To illustrate the type of parts that are in aluminum in battery electric vehicles today, this slide shows some pictures of where it's used. So the battery enclosure itself is heavily aluminum intensive. It typically consists of multiple parts of stamped sheet, of extruded profiles, and also some castings for a typical weight around 150 pounds per battery enclosure. As I said, there are some smaller casings and castings in the component, but importantly, there's a lot of aluminum in the body in white, both as structural castings, as extruded profiles, and as auto body sheet. And the closures are dominantly made in auto body sheet and aluminum, sorry.
Andreas, I have a quick question here. The exploded view that you show in this, the cooling system, it looks like it can have a liquid cooling.
Yeah,
for
so
the
this is a liquid cooled. So it's in this case the cooling system is made of extruded profiles with little holes in them. Mm-hmm. So the cooling liquid is pumped in to extract the heat. Okay. The thermal management system can also heat the battery, so it works both for heating and for cooling.
Thank you.
Yeah, then looking specifically at the material choice in battery enclosures, we plotted out here the battery electric vehicles that are on the market today. You see in this chart the name of each vehicle against the range, how far they can go on a single battery charge. And then this has been color-coded to show the main material for constructing the battery enclosure. So blue means it's an all aluminum battery enclosure. And the orange color means it's all steel. Green means it's a mixed material construction. And black refers to these two carbon fiber composite battery enclosures that are used in these two electric super sports cars from McLaren and Aston Martin.
So in this chart, it seems like you know, a large number of vehicles today have aluminum battery enclosures structures, but I also see steel, a lot of steel, very few carbon fiber. Only 2 vehicles you show a carbon fiber, and also mix. So do you think there could be more mixed material designs in the future? More of green in this chart?
Yeah, so I think when you look at this same chart in 10 years from now, it's probably going to look quite different. And in a few slides out from now, I'll try and explain why this is. So I think the main thing you can take away from this is all the long-range vehicles today, those with a range of more than 250 miles or 400 kilometers, they have chosen to use aluminum. Mm-hmm. For the much smaller sort of city electric cars with a moderate range, you see a much more mixed picture with some steel, some aluminum, and some mixed material. So I think what we say is in the future, this trend is going to slightly shift up.
Okay.
Yeah, so now that we established how much aluminum is used in battery electric vehicles, I'll try and go through the drivers for the material choice to explain why this is. So when discussing the choice of using aluminum for constructing automotive bodies, it's important to know that this is always about the lightweighting aspect of it. So there are many good properties in aluminum, but the main reason for using it for constructing cars is that it allows for lightweighting. And for this, we also need to understand the concept of primary and secondary mass saving. This means when you design a component or the body structure in aluminum, the total weight of the vehicle goes down, and you can then resize your battery and your powertrain and still get exactly the same performance you had before. So this is the secondary mass saving. When you resize the battery and the powertrain, you also have less mass that you need to account for in crash situations. So you can further downsize the body structure. So this is like a virtuous circle of lightweighting. And this, of course, has impact not only on the performance, but very much so on the cost. So in the next few slides, I'll try to explain what is the impact of aluminum lightweighting on the performance, how does this correlate to impact on the cost, and also how does it affect the sustainability of the vehicle in terms of the carbon footprint over the life cycle of the car. So when we talk about the performance of battery electric vehicles, we should remember that the basic physics of the forces that needs to be overcome to move the car, it doesn't change even if we change the powertrain. So of the three main resistive forces, of the four main resistive forces, three of them are directly mass dependent. So rolling resistance, the resistance of going up a hill, or the resistance of accelerating, all goes up when the mass of the vehicle goes up. And I think everyone who works in auto body engineering will agree that a lighter vehicle body always gives a better sort of overall balance of these key performance criteria in terms of range, driving dynamics, acceleration and handling, fuel or energy consumption, as well as the towing capacity or the payload you can carry. The second thing that most body engineers will agree with is that an optimized aluminum design for a part or for the body as a whole is roughly about 40% lighter than an equally optimized steel design. So you can get a much lower number if you choose to compare a brilliant steel design with an obsolete aluminum design, and you can get a much higher number if you do the other way around and compare a very old-fashioned steel design with a state-of-the-art aluminum.
So this 40%, Andreas, is compared to which grade of steel? Mild steels or the higher grades of steel?
So that includes the higher grades of steels. So it's just like steel have developed several generations of advanced high-strength steels, there are new generations of aluminum alloys and aluminum solutions that match these pound for pound in terms of strength versus weight.
Okay.
Then on this concept of secondary mass saving, it's true that a heavier steel-bodied electric vehicle, it can have exactly the same range as a light-bodied aluminum design. You just have to incrementally increase the battery. You can also get the same acceleration, but then you have to put more horsepower or put a bigger electric motor in so you can get the same performance. This is the secondary weight gain. And by doing this, you get the range and the acceleration, but you do compromise then on the energy consumption, which means you're going to have to spend more time charging the car, and you compromise on the driving dynamics. It's no longer so much fun to drive the car. It's big, heavy, hard to handle. In terms of quantifying this, there was a recent study published by Hydro Aluminum carried out by the IFA Institute in Germany. And they showed that if you start with the aluminum intensive from mid-size long-range electric SUV, and you substitute aluminum parts with steel to save money in a way that you add 100 kilograms of primary weight, you would then need about 3.5% bigger battery and about 6% more powerful electric motor to match the range and acceleration. So you save some money on substituting aluminum with steel, but the question then is, you need a bigger battery, a bigger motor. Did you really save money in the end?
So I have obviously not read the studies so far, but this is very interesting data point. Though I would like to know, what battery density they are considering, because the battery manufacturers are working and putting a lot of R&D funds and improving the batteries. And when the battery improves, like if they are able to double the battery density what it is today, then will this percentages still hold true?
Yeah, and I think you are quite right in that. It depends very much on what was the battery cost and the battery energy density at the time you made your material decisions. Mm-hmm. So this brings me to the point of cost. And while this is all new and exciting technology, we are still in the automotive business, and cost is king. So the car makers, they will always choose that solution that gives the best compromise between performance and cost. So I think I got the point across that the value of lightweight design with aluminum is not in terms of comparing the raw material cost or even the cost of the component. I think we all agree that aluminum is more expensive than steel, and aluminum part or aluminum body made from aluminum is also going to cost more than the steel body. So then the justification for this overcost is always going to be in the secondary mass saving and the secondary cost saving from being able to downsize your battery and the powertrain. So as you said, battery cost has seen a dramatic evolution over the last decade. It's fallen in price almost by a factor of 10. So if it was $1,000 per kilowatt hour in 2010, I think last year it dropped below $150 per kilowatt hour. And as you also pointed out, the energy density has almost tripled over this same period. So a battery that 5 years ago was very heavy and incredibly expensive now is much cheaper and it weighs much less. And as with most things, technology, there's no reason to think this is not going to keep improving and cost keep going down. So I think this goes a long way to explain why we see all the long-range battery electric vehicles that you can buy today using aluminum is because at the time they were making their engineering choices and the material choices, this equation was super simple. You spend a few $100s more on the body structure and you save thousands of dollars on downsizing the battery. But as you say, when these prices go down, that equation is no longer so obvious. So we think today, at the current prices, it's still strongly in favor of aluminum design, especially for the big vehicles, so SUVs and pickup trucks that target the long range. But soon, it may no longer be economically beneficial to use aluminum, especially for the small cars that have moderate range and really target the lowest possible price point. So we think we will lose some market share there, and you see more steel design or multi-material design. So the only thing,
Andreas, before you go to this slide, there are some good questions coming in. Uh, one of them is, what about the second order manufacturing consideration, like joining technologies, dealing with corrosion, mixed material designs? Can you talk a little bit about how does aluminum battery enclosure design address, like how is it joined? What kind of joining technologies do you use? And then what about corrosion issues?
yeah, so I think um, today aluminum can be joined by a very wide range of joining technologies, pretty much as is available for steel. And I don't think there's any significant overcost in the joining of our all aluminum enclosure compared to that on steel. So typical joining technologies is MIG welding, laser welding, also mechanical joining combined with adhesive bonding. So self-piercing rivet with adhesive is commonly used. In terms of corrosion resistance, aluminum is inherently much more corrosion resistant than steel. You don't need any coating or any protection to use aluminum in a battery enclosure. It's resistant to all sort of environments.
Okay, thank you. One more question before we move to the next slide. What level of serviceability is expected in aluminum battery housings and covers? Do your customers expect to service the battery enclosure in the vehicle lifetime? Do you expect what kind of serviceability can you expect from the aluminum designs?
Yeah, so the battery enclosure itself should last for the full lifetime of the vehicle. So the enclosure should by far outlast the batteries inside. So there should be no need for replacement or servicing.
Okay, thank you.
Yeah, so as I said, the only driver that could upset the sort of simple logic of performance versus cost is the sustainability. And by sustainability for battery electric vehicles, we talk about the life cycle carbon footprint. So how much CO2 is emitted over the lifetime of the vehicle, looking both at manufacturing phase, use phase, and carbon credits for the end of life recycling phase. So life cycle analysis is a type of accounting. It is best when it's done by international standards like the ISO 14040. And it's also best when it's done by independent, unbiased bodies who don't have a direct interest in the outcome of the analysis. So today, I'm not aware of any unbiased and detailed study that looks at the carbon footprint impact of material choice in battery electric vehicles. But I know there are many biased studies. So, for example, colleagues in aluminum industry have published studies that show aluminum is great and has the lowest carbon footprint. There are many steel company and steel organizations like World Auto Steel have published their studies showing that aluminum is not at all good and steel is the best material for carbon footprint. And I'm sure our colleagues in polymer industry have their studies that say exactly the same, that they are the best. I think the only thing we all agree is that magnesium has the worst carbon footprint of all materials. Anyway,
on that, Andreas, there's a question from the audience.
Yeah.
Are there any magnesium designs for battery enclosures?
I haven't seen one.
Okay.
Yeah, I'd be a little bit worried about the fire resistance, but
Right.
Yeah.
Thank you.
As I, the reason why it's possible that two companies do essentially the same life cycle analysis and they come up with completely opposite answers is that this depends hugely on the assumptions you make in the input data, particularly in the assumptions about the embedded carbon or the CO content or CO2 content of the raw material, as well as the assumptions you make about end-of-life recycling rate and how much CO2 is credited in the end-of-life recycling. Now, the CO2 footprint of aluminum can be confusing even for people who work in the aluminum industry. So it's almost forgivable that people make mistakes and use the wrong reference data. And this is all because primary aluminum is made by a process called electrolysis, where we use large amount of electricity to convert aluminum oxide to the metal form. So how much CO2 is emitted when you make a kilogram of aluminum then depends hugely on how this electricity was generated. So if, like is commonly in North America, the aluminum smelters use renewable energy from a hydroelectric power plant, the amount of CO2 emitted is not very high. It's about 4 kilograms per kilogram of aluminum. If, on the other hand, the smelter is powered by inefficient coal-fired power plant, which is sadly still the case in most of the Chinese smelters, the CO2 content of that aluminum is much higher at 20 kilograms or more per kilogram of aluminum. And the last thing is, if the aluminum you use is not from primary metal, but from recycled scrap, this requires just a fraction of the energy to remelt and produce than the primary metal. So there's only 5% of energy needed to recycle aluminum compared to making it in the first place. So recycled aluminum has a carbon footprint of only 0.5 kilogram. And the other thing to be aware, and you should include in your calculations, is that aluminum in automotive applications in North America is effectively recycled at the end of life. So 96% of the aluminum that goes into a car is recycled and put back into full value products at the end of life. This is one of the benefits of being an expensive metal, is people will go to great lengths to extract the scrap and sell it for a good price on the scrap market. And this brings us to the first poll question that we wanted to ask the audience in this presentation. So you should see popping up on your screen multiple choice. So we want to know, for you personally, which criteria is most important in terms of making you choose a battery electric vehicle over an ICE or a hybrid car next time you buy a vehicle. So do you want longer range? Do you want reduced charging time? Do you want the vehicle that has the lowest possible CO2 footprint? Or you only care about cost and will buy a battery electric vehicle only if it's cheaper than the alternatives? So I think we're gonna have about 1 minute to answer. So we submit this now.
And while everybody is answering the poll, I have one or two questions from the audience that I would like to ask you. Do you see any aluminum hydroform applications in the aluminum box structures? Hydroforming.
No, I haven't seen any hydrophone parts in a battery enclosure.
Okay. Here we see the results.
Oh yeah, there we have the results. Yeah, so it seems the most important performance criteria is the longer range. And people really don't care that much about the sustainability impact. That's interesting. Otherwise, it's relatively equal between the other answers. Okay, great. That's very interesting information to take with me. Okay, now I will talk a little bit more in detail about the battery enclosure, how it's designed and what kind of materials we are using today, as well as some things that we are developing for the future. So one of the main functions of the battery enclosure is to protect the battery cells against intrusion in case of crash, other kinds of impact. So it's designed as a very strong box that doesn't allow intrusion in a way that could short circuit the battery cells, because this could cause a thermal runaway and a fire. So the sides are protected against crash and side impact. The bottom is protected against driving over road debris or driving onto something hard. And the top main function is to protect the passengers in case of thermal runaway or fire. So it should survive for long enough that the passengers can evacuate the car if it starts to burn. The battery box also has a thermal management wall. It needs to have included a heat exchanger system that allows you to both heat and cool the battery cells so they can run at an optimal capacity, and also protect the lifetime of the battery. The battery enclosure also provides a sealed function, so it has to be completely watertight so that no corrosive atmosphere can get in and damage the batteries. And it also should act as a Faraday cage, so shielding from electromagnetic radiation that could interfere with the other electronic parts in the car. And it must also have the necessary corrosion resistance and bond durability to last for the full lifetime of the vehicle. Then finally, the battery enclosure is a part of the car body structure. So it has to be able to be correctly integrated in the vehicle and meet all the stiffness requirements, etc. There may also be modularity requests. So one battery enclosure should be able to accommodate different battery sizes for different models of the same vehicle. And of course, you have to respect the necessary volumes, the allowable dimensions, and all this should be done at a minimum weight, but meeting your cost target. Then looking specifically at the main aluminum parts in the enclosure, you have the top protection cover. The main function here is to seal and also to act as this firewall in case the battery starts to burn. Today, this is mostly made in high formability stamped aluminum sheet. It does not have very high strength requirements. Then comes the structural frame and the cross members. The main function of these is to protect the cell in the case of crash intrusion. This can be made in stamped sheet or roll formed sheet, but in aluminum is most commonly and most efficiently done in extruded profiles. The material requirements here is for very high strength, combined also with parts that need high strength and high ductility to be able to absorb crash energy by controlled deformation. Then is the thermal management system, which is usually a cooling plate. This can be a brazed sheet solution, or it can be extruded microport profiles. It can also be integrated into the bottom cover. The bottom plate, the lower protection cover, this is the one that protects from undercarriage impact. If you drive over a rock or something, is usually made of sheet, but it could also be made of welded extruded profiles. And the sheet can be either just flat and joined to the frame, or it can be stamped into a tray where it also adds to the sealing function. The material requirement for this, I'll go in more detail in a little bit, is high strength combined with high ductility. So looking at the sheet aluminum alloys that are used in battery enclosures today, these belong to the 3000, 5000, and 6000 series, with the most commonly used being the 6000 series, aluminum, magnesium, silicon, with optional additions of copper. These are heat treatable alloys, means they have very good formability in the soft T4 temper, and then they gain a lot of strength through heat treatment, either the paint bake treatment of the vehicle or by separate sort of peak age treatment called post-form heat treatment. These alloys can reach 300 megapascal in service yield strength with very good crash ductility, or 350 megapascal or a little bit more with reduced ductility. The 5000 series alloys are non-heat treatable, so they do not reach the same strength levels, but they also have excellent formability and can be strengthened by cold work to strength levels like 250 megapascal. For strength levels beyond 350 or 400 megapascal, it's necessary to move to the 7000 series of alloys. These are aluminum, zinc, magnesium with copper, which is the highest strength alloy family in aluminum. These are not yet widely used in automotive, but vehicles like the BMW i8 has one part in 7075, and the recently launched Neo ES6 contains 7 parts of hot stamped 7075 with this 500 megapascal in service yield strength. Specifically for assessing the resistance of the bottom plate to impact, we have developed sort of an in-house test protocol and a simulation tool where we look at where we clamp a piece of the test material in a firm fixture and then indent to 15 millimeter depth in different positions and look at the force for this penetration. This allows us to, for comparing different alloys and tempers, we can then determine an equivalent gauge in impact resistance and therefore the potential for light weighting.
So this bottom plate, this is, you see this made out of the 7000 series in the future?
I'll explain to you in one slide. So I think the answer is probably no.
Okay.
And I'll try to explain why. So this table here shows alloys that are currently in use for bottom plate in battery enclosures. So you have soft temper 5000 series, hard work hardened 5000, and then the aged 6000 series alloys with the highest strength. If we compare the impact resistance and you use the soft 5754 as the reference, we see how much down gauging or weight reduction we can get by moving to higher strength. So we see the higher the strength, the lighter you can make it. However, there's also a stiffness factor in this. So once you go beyond a certain strength level, the weight benefit is of diminishing return. So when we go from 300 megapascal in 6000 to 500 megapascal in the 7075, we only gain an additional 10 percentage point of lightweighting. And so we think at the moment, with the way things, with the manufacturing processes needed, this small benefit probably doesn't cover the cost of using 7000. We are working on an alternative alloy where we change the stiffness or the modulus of the alloy by adding large amounts of silicon particles in it. So you get this sort of metal matrix composite effect with increased stiffness. We see that then that you can heat treat this to a strength level that allows the same lightweighting as the 7075, but in a solution that is compatible with normal cold forming and at a much more competitive cost.
So Andreas, there's a very interesting question from the audience, which we were also discussing before we began the webinar, on moving from battery enclosure as a separate subsystem to including that into more sort of a structural part of the vehicle, and sort of like a unibody construction. So if that trend happens, we've not seen it yet in production. Do you see similar alloys being used in that sort of construction? Are you even seeing that trend?
Yeah, so I also think the concept of putting the cells directly into the chassis or directly into the body in white is very interesting, and it certainly removes some of the redundancies of having this box inside the box. But still, in this case, the material requirements will be exactly the same. So I think we will still see the trend towards very high strength for stopping intrusion, and the need for strength combined with ductility to absorb energy by controlled deformation in the case of a crash. So yes, I think we can see much lower requirements on the battery enclosure itself, because a lot of this function is being taken up by the rest of the vehicle body.
Okay. Yeah, let's finish the presentation, because I have a lot of questions, good questions from the audience.
Yeah. Then for extrusion alloys, the common way to sort of represent them is not in the banana chart I showed for sheet, but as in-service strength compared to an extrudability or manufacturing index. So this shows this strength level versus manufacturing index for sort of standard industry alloys, also the 6000 series. And you see some of the alloy chemistries that are used in extrusions are the same that I showed for sheet. And in common industry alloys, it is you can get 6000 series alloys up to about 300 megapascal in service strength, but beyond that, it's common to switch to low copper 7000 series alloys, where you get alloys like 7108, which can reach close to 400 megapascal strength. In Constellium, we have developed two families of proprietary alloys in the 6000 series that is optimized for strength. The HSA6 family solely focus on strength and do not have the ductility for crash crushability, but they allow, by combining modified alloy compositions with modified extrusion practices, we have products that go from 300 megapascal strength in service with very good extrudability and the ability ability to make complex shapes, up to 450 megapascal in service strength. But then, of course, with less flexibility in the shapes that can be made. The HCA6 family are crushable alloys that have strength combined with very high ductility to be able to deform and absorb the energy in crash. So an example of the benefits we get from these new families of alloys, we look, this is like a dual material frame concept. So you have on the inner part, you have a very high strength extrusion that's only there to prevent intrusion into the battery cells. And then you have this outer frame reinforcement made of a ductile material that's there to protect the passengers by absorbing the energy in case of a crash. So if we say the reference for this would be to use a standard alloy like 6063 with a strength level of 240 megapascal, you could gain 20% of weight saving by going to 290 megapascal solutions with this new alloys and maintain a very high extrudability. You can also go with a sort of modified heat treatment at the end. You can reach strength levels of 330 megapascal and additional weight saving of 35% versus the industry standard reference. So this just to sort of say that aluminum design is not one thing. There are multiple new grades coming on the market that will allow continued improvement and keep aluminum sort of competitive on the lightweighting versus new material solutions from steel or polymer composite. So to summarize, what I wanted what I'd like you to take away from this is that aluminum as sheet and extrusion profiles is today the preferred and by far the most used material for battery enclosures. And typically you will get a weight saving of 40% if you compare aluminum design to steel design. This lightweighting gives you a better balance of properties, and it also gives this secondary mass and cost saving by being able to downsize the battery and the motors and other parts of the structure. And on the sustainability side, you should know that aluminum is infinitely recyclable, and there's no loss of property no matter how many times you recycle it. And automotive aluminum is recycled to 96%. And this requires only 5% of the energy needed for primary production. So the aluminum that's used in North American automotive parts is made from a mix of recycled metal and a metal sourced mainly from renewable hydroelectric energy.
So on that note, there are a couple of questions on sustainability. Do you see LCAs becoming a decision factor for material selection in the future? And then how significantly does the CO2 emissions change as you go up from that 5,000 series to the 7,000 series in the future?
That's a good question. I haven't thought of that before. On the first point, I think we will see at some point a shift away from legislation on tailpipe emission towards legislation on life cycle analysis. I think this makes sense once you have an increased share of electric vehicles. On the second point, there is no impact of the alloy or the alloy family on the CO2 emissions. So that's entirely dependent on the primary production of aluminum.
Mm-hmm. And coming to the safety part of the battery enclosure, right now there are no federal regulations that I am aware of, and everybody is testing their own standards. So do you expect federal regulations around the battery enclosures, and what sort of safety criteria in your view should be industry standards?
Yeah, so I am not sure there's going to be federal regulation on the battery enclosure. I think there will be on the vehicle. If anything, the one thing I would expect is this firewall or the protection of the passenger cell in case of fire. But I don't think the battery enclosure itself is going to have a separate legislation.
Okay. Um, so how is Constellium design different than the aluminum designs of other suppliers?
Yeah, so in fact, what I've shown in this presentation is not specific to Constellium designs. I'm talking more generally about aluminum battery enclosures. I'm sure our teams are maybe a little bit more clever than our competitors, but yeah, I don't think there's a fundamental difference in how we design battery enclosures to how other aluminum companies do.
Uh, you mentioned that aluminum doesn't require any specific corrosion resistance coating, so they do not. So there's no need for anodizing. That's the question.
Yeah, that's correct. So the 5000 and 6000 series alloys that are used today for battery enclosures, they don't need anodizing, they don't need e-coat, and they don't need any sort of conversion coating. They are very resistant to road salt or any kind of environment.
Okay. And would the recycled aluminum material reduce in quality or stability compared to the new material?
No, so it doesn't, and there is no way that you can tell that aluminum component is from recycled material or not. Is once you remelt it, it wipes the history, and it's like brand new.
All right. There are a lot of other questions which we will answer through email. Andreas, if that's not an issue, I will send you the questions, and
I'd be
we
very
can,
happy to, yeah.
yeah, we can send an email to all the attendees today. But thank you so much, Andreas, first, for presenting this great content. It was a really good discussion, and thank you everybody for attending. This is the first one in the series. There are two more webinars coming up. The other one is next Thursday, where we will hear from Hexion. So yeah, see you next week. Thank you, everybody. Have a nice day.
Thanks a lot.